Okay, so today, as a final topic, I want to discuss connections with algebraic K theory. So wherever basically motives appear, K theory appears as well. And I guess, we'll see how it appears. So far we've discussed maybe these higher Chow groups. So for some codimension I, given some nice scheme X, I can look at some codimension I closed subvarieties in cohomology J. These are some kind of blocks, higher Chow groups, which we have defined and studied in some sense. And maybe, we have also seen motivic cohomology, so maybe something like H 2i minus j x zi. I changed the indices here because I want to make them equal. And maybe one of the main theorems is that these are isomorphic. So here we have motivic cohomology. Okay, and maybe in Bloch's 1987 paper, so in Bloch's paper on where he defines these CHXJ. At that time, motivic cohomology was not really available as a type of machinery, but he studied K theory, so he proved the following facts. So he proved that let's say for X quasi-projective, and smooth. He proved some generalization of Riemann-Roch. So on the one hand, he had his higher Chow groups rationalized. So these are like some kind of Z modules, summed over all over all codimensions, and this was the same. So this is a result of Bloch as these K groups. KJX, maybe rationalized as well. Okay, so for today's talk, or for today's lecture, I want to discuss basically what this object is. So why is this, first of all, a kind of generalization of Riemann-Roch? Maybe, Riemann-Roch is a very old theorem, maybe more than 150, maybe 130 years old or so. But Grothendieck then generalized it to include this K0 group. So K0 is basically after Grothendieck. Which is basically projective modules. As a free group. And using this K0, he could classify, say, points. So you don't need to do all codimensions here. Just I equals n is enough, which n is the dimension of X. So this then leads to so-called Grothendieck Riemann-Roch. And then people so this is on the algebraic side, And then people from topology, they kind of took his definition of K naught, and in topology, this was kind of seen as kind of the starting point of some homology theory. So they extended the definition to higher I. So, but the trick here was to use maybe the sphere spectrum wedged with maybe X, where this is K naught X, maybe something like this. So you have access to, say, suspension functor. So this is, so far maybe something like algebraic, topological K theory, where your underlying spaces are topological spaces. And the idea is you kind of, K theory should be something like, or all higher K theory, let's say, should be something like some kind of homology or cohomology of the space, some space of vector bundles. Bundles over X. And vector bundles may be in topological sense, when X is just a topological space and no algebraic structure, maybe it's a bit easier. They're kind of easier to study just because of you have more access to more operations, including the suspension functor. But on the algebraic side, it took far longer to come up with the right definition. So there are several definitions of what algebraic K theory is. And today I want to kind of discuss the modern definition. So maybe a definition that's not more than 10 years old, let's say, or something like this. Okay, but let's start with, it's easy to define the first few K groups. So like K naught is easy, K1, and then because you have this homology of some kind of space of vector bundles, to construct this space of vector bundles, okay, maybe one version would be something like the homology of the category of vector bundles, but that's kind of not real. It's not quite right. Maybe not enough structure on the category. One candidate for what this space should be is, so candidate for this space is something like the derived category of vector of maybe R modules. And because we want vector bundles, it should be projective R modules. Projective is locally free, right? Okay, maybe this is like, why do we need to go to derived category? It's not clear at this stage. But certainly like homology, I mean, that's some kind of higher notion of like your connected set. So K naught maybe should be something like number of connected components. Components of maybe this category here, whatever this is. This is loose so far. And maybe taking intuition from what topology is, like Kn, maybe it's something like higher homotopy groups. Groups of this space. And we don't really have access to this notion of higher homotopy on the algebraic side a priori, but we do once we pass to infinity categories. So infinity categories, yeah, they're maybe very close to topological spaces in some sense. And there is a well-defined notion of what it means to take the nth homotopy group or higher homotopy groups of these guys, mimicking what happens in the case of topological spaces. So something what we're aiming for here, like mimicking from what happens in topology, is something like the higher homotopy, the nth homotopy group, where we're looking for the nth k group of some derived category of X, let's say, where this derived category is something like finite projective R modules, if X, for example, is spec of R. Something like that. So, but yeah, we'll see roughly how to do the higher K groups. But certainly to start with K0 and K1, like mimicking connected components and just like loop groups, you can do it on the nose without much machinery. Let's start with this. So K0. So this was like easily defined, I guess. Well, not easily, but it's a definition due to Grothendieck. And it was just to make his Riemann-Roch theorem work. So the definition is as follows. So for R, a ring, which is commutative with a 0 and 1, you can define, K0 R is defined as follows. So remember, it should be kind of connected components of your projective R module. So one natural candidate is to take the free group of finitely generated R modules, finitely generated projective, sorry. Okay, we're trying to study vector bundles here. Quotient out by exact sequences, so maybe P plus Q is equal to PQ. I can write this in this way. I mean, because exact sequences split in projective R modules, so this is equivalent to saying exact sequences are 0 in some sense. And so one thing to note from here, I guess, is the following. So K0 R satisfies the following fact. So satisfies the following. This is as a hint for a candidate definition of Kn. So on the one hand, we can write homomorphisms as abelian groups of K0 R, let's say A, is the same as homomorphisms between commutative monoids from this proj R, which I will define in a moment, to R, and this guy proj R is basically isomorphism classes of finitely generated projective R modules equipped with some addition operator, so maybe with an addition operator, where you take maybe P plus Q is defined to be just the direct sum. So basically, in this way, K naught is the closest group-like maybe functor, which represents these functors in some way. So yeah, higher Kn groups due to the modern definition will be some kind of similar version of this. Okay, before we get to higher K groups though, but we can look what K1 should be. So it was observed like fairly early on that K theory should satisfy some kind of descent for closed covers. So recall, like for example, we had like the CDH topology, which had formal blow-up squares. Blow-up squares as covers. So K theory satisfies descent for the CDH topology, but this is like kind of maybe a bit of an advanced statement. But down to earth, K1 at least the K1 group, which was defined fairly on, satisfied some kind of descent for closed covers, not quite living in the CDH topology, but what is now known as maybe the CD arc topology. So this is a fairly new topology. Maybe arc topology was defined in 2020, and CD arc also fairly recently. And some covers here so-called Milnor squares as covers. And but this notion of Milnor square is due to Milnor from way back, not 2020, but maybe formalized very nicely in this so-called CD arc topology. But let's recall that maybe in any case K1 satisfies descent for this huge CD arc topology, let's say, and in particular for Milnor squares. So let's recall the definition of, not recall, but let's see the definition of a Milnor square. I just wanted you to keep in mind that in modern language, there is something called the arc topology, and that's where kind of Milnor squares sits very naturally. So Milnor square is basically something that looks like this. So you have a morphism of rings, R to S, and some ideal in R, which maps isomorphically to an ideal I, which will continue to denote by I in S. So this gives rise to like this commutative square. And and this, this is what a Milnor square is. Something that occurs in this way. So recall, I must be mapped isomorphically to S. And somehow, like, you see, like, geometrically what's happening here is like we're taking closed covers here. So this is like a closed set of this, so is this of this, and it's not quite a formal blow-up square, but this can be made into some kind of covering notion which lives here. Okay. But something was observed, I guess, by Milnor very early on, which is the following. Here, so given a Milnor square, there is a long exact sequence. So as I mentioned, K theory satisfies descent for this Milnor square, and the way to write it is as follows. So you have k naught of R mapping to k naught of S, direct sum with k naught of R over I, and this maps to k naught of S over I, and this term appearing here is this so-called GL infinity S over I, where this GL infinity S over I is a union across all GLNs. Wait. S over I. So the hint here is that K1, so it should be, K theory should be some kind of homology theory, so there should be some long exact sequence coming from the descent datum of a Milnor square, which starts here. So K1 should be related to this somehow. And the precise definition that people came up with is the following. So definition, K1 of R for ring R is this GL infinity of R, quotiented out by the commutator subgroup. So, yeah, I didn't really define what this map is, like here, but I guess in the literature maybe it's called patching map, but let me not define it. Okay, and with this definition of K1, we indeed get a long exact sequence with K0 and K1. So theorem, given a Milnor square. So this is like think of Milnor square as like a baby kind of cover living in some big site, which we don't know yet. Well, so we have these K naught S plus K naught R over I maps to K naught S over I, K naught R. Okay, and this sequence extends using K1 now. As one kind of expects. Okay, so yeah, like this, I mean, it looks like it's so far some kind of right definition, the correct definition. And before we go to higher K theory, like K2 and so on, there is like negative K theory, which should be something that appears here, right? So maybe K minus 1, like whatever that is. So here we have negative K theory. And this is also relatively easy to define without using any kind of heavy machinery. So maybe, wait. So maybe let's look at negative K theory very quickly. So the hint for what it should be is as follows. And it's called maybe fundamental theorem for K1. And it's as follows. So for R a ring, there is an exact sequence so from 0 to K1 of R, and then to K1 of R adjoined with some variable t plus k1 of r adjoined with some variable t minus 1 mapping to k1 of r t minus 1 and mapping to k naught of r mapping to 0. So yeah, I mean, okay, maybe it's a bit of a random theorem, I agree. But it gives the correct definition for negative K theory. So we can define for n greater than 0, define inductively K minus n r by the following. So K minus n of r is, so we can have these maps K minus n plus 1 of r of t plus K minus n plus 1 of r of t minus 1 mapping to K minus n plus 1 of r of t minus 1, and we take the co-kernel of this map. Okay, so this is like based on this fundamental theorem for K1, which I agree is maybe somewhat random. In any case, with this definition of negative K theory, we get maybe some theorem, so sanity test for seeing whether what we've defined so far, so K2, K1, oh sorry, not K2, K1, K0, K minus 1, K minus 2, and so on. We're seeing whether it makes sense. So for Milnor squared, at least this is what was historically thought to make sense. So for Milnor square, R, S, R over I, S over I, we get a long exact sequence. So K1 of R to K1 of S plus K1 of R over I to K1 of S over I, and then it continues to K naught of R to K naught of S plus K naught of S over I. I think, by the way, the definition of Milnor square that I gave, you can check that it's a push-out square. But yeah, I think so. So this continues K naught of S over I, and so on. K minus 1 of R, and so on. Okay, that's maybe some sanity test. Okay, now we move on to higher K theory. So for K greater or equal to 2. You don't have to use as infinity categories, I guess. You can use some other, maybe Quillen's construction, but I want to talk about maybe the modern definition. The modern definition kind of uses Lurie's infinity categories. I briefly recall some things, but yeah, I'm not expecting everyone to know infinity categories, but you can certainly ask questions if you want clarifications. First thing is like, so far we've been dealing with like for a ring R, right? And for ring R, we've kind of associated these KR groups for low dimensions, let's say. And the whole, maybe to correctly kind of work within this setup, you have to replace everything with categories. So you can't just work with a ring. And as I mentioned, like maybe one candidate here would be the category of projective R modules or something. So something like the K-theory of the category of projective R modules. Somehow like, yeah, there's just like not enough substance here to do homology, and it's better to move to something derived. So something like the derived category of this category. So of this thing. And the whole derived category is a bit too big, so it's better to work with the bounded derived category. So if you just work with the usual derived category without any infinity category setup, you run into some issues. So here's the issue basically. So in DBR, so just to make sure, this is the bounded derived category of the category of finite projective, finitely generated projective R modules. So a typical element up to equivalence maybe looks like something like this, like 0 coming in, and then something like some finite projective R module. Okay. But this is up to isomorphism, so you have to be careful. In any case, you get the following issue. So you can think of take the map from R to 0 and consider its cone. So this is just R of 1. On the other hand, you can also take the map from 0 to R and consider its cone, and it's also R of 1. And here, both of these maps are 0. However, there are two possible maps here. Like either you can make 0 or you can make identity. And the cone, is some kind of limit. In this case, injective limit of some diagram. So typically you want limits to satisfy some kind of functoriality property. In particular, there should be a unique map going from, given some diagram, which is this, a priori, you can take the limit of this diagram and the limit of this diagram, and limits say that like, if I have a compatible system of maps from this part to this part, there should be a unique map from the limit of this to this. And here there are two. So you have issues of functoriality. In other case, this is definitely not a limit in the usual sense. And one way to fix this is to work with infinity categories. So basically, infinity category at the very, very naive level is like to add more morphisms between, here we are considering one morphisms, but you should also consider morphisms between morphisms. So in this diagram, yeah, if you one should also keep track of the morphisms between here and the morphisms between here, and they should also satisfy some compatibility. In any case, like once you wrap up all these morphisms together, between morphisms, this then really does become a unique thing, up to all morphisms between morphisms, which sounds a little bit, not very, very loose, I would say. But in doing this, you end up with an object which we continue to denote by, say, dB of R. And this is now an infinity category. It basically has the same objects as dB of R classically here, but more morphisms. Is particular, not morphisms, one morphisms, let's call these one morphisms, but morphisms between like two morphisms and three morphisms, and so on. And you can kind of recover the usual naive dB of R as some kind of, for every infinity category, there's an associated usual underlying one category, and the underlying category is the naive thing here. So because we want like to construct K-theory in a functorial way, we kind of forced, and because kind of we want to work with derived categories because they're kind of nicer from a homological perspective, we're forced to work with some infinity version because K-theory should be some kind of functorial mapping. And clearly functorial here fails dramatically if we work with just the naive thing. So we have to move to infinity categories, and now I kind of define like the basic setup for that. Here are the objects that we need. So cat infinity will be the infinity category. I mean, it will take like, it takes basically an entire lesson to really define properly what infinity category is. But for now, let's just keep a naive thing that it's like morphisms between morphisms, higher morphisms. But now we can we take classical categorical constructions and you can package them up in a correct way to form infinity categories. So there's this object called cat infinity, which is an infinity category of infinity categories, basically. Or maybe small, right? I mean, otherwise you'd run into some issues of ordinality and things. So this would be like the analog of maybe cat in the literature for this is the usual one category. But this can also be made into let me not get into that. But you can package up all small categories into a category called cat. There's also some object called the cat spectra, which is basically the infinity category of abelian groups of the category of abelian groups. And then there is this category of maybe these days after Schulze called anima, which is the infinity category of groupoids. And groupoids is basically, these are infinity categories where all one morphisms are invertible. So there are forgetful functors. So first of all, a forgetful functor from, let's call it dash group, which goes from cat infinity to my infinity category of monoids, this anima, which basically forgets all one morphisms which are not invertible. So forgets all one morphisms which are not invertible. And there's also a forgetful functor associated with this spectra, which is called omega infinity, I guess mimicking what happens with spectra in topology, going from spectra to anima, kind of forgetting the abelian group structure and just thinking of it as a monoid. And the reason why I'm talking about monoids here is because K-theory, remember that K naught was kind of the closest group-like functor, which somehow keeps track of AN. So just as kind of a spoiler or something to keep in mind of what K-theory will be, maybe a quick definition of K-theory. It will be basically functors. So you consider the category of functors F from cat infinity to spectra. So some abelian, K-theory, you expect it to be an abelian group. So for every kind of nice category, in particular think of like dB of R, which is what we've been talking about, you should be able to get some kind of nice abelian group, which should lie in spectra. So you have this category of functors F, which are equipped with a transformation so I can think of this functor groupoid dash group, and it gets sent to omega infinity composed with F. So let's just go through this again. Consider the category of functors F, which map your favorite category to some abelian group in a functorial way, which are basically equipped with, when you forget the abelian group structure, and think of it as just a groupoid, so in particular living in N, anima. So this is like forgetting the group structure. And this transformation is, just basically keeping track of that it's maybe not too crazy that what this functor is doing. And basically K-theory will be the initial object of this category. So it'll be the limit of all objects in here. So it's some kind of universal functor K from cat infinity to spectra, which maps to every other functor with this property. But due to some technical issues, we can't really work with cat infinity. It's a bit too big, and it doesn't satisfy enough descent properties. It's not clear that this category has an initial object. So to cut out an initial object, we also need to work with this guy, a version of this guy, which satisfies enough descent properties. And for maybe the next part will be kind of refining this to find a category of categories which is still big enough, which contains dBr, let's say, and but satisfies enough descent so we can find an initial object in this space. So I don't know if there's any questions up to now. I mean, everything has been a bit loose, I would say. Okay, but let's continue. So here, the goal may be for the next part, find a refinement of cat infinity so that the category of functors from cat infinity to spectrum has enough descent properties. So that we can cut out an initial object. Well, and this initial object will be K theory. Okay. So here we need to work with stable infinity categories. So definition of stable infinity category. So Lurie has several works on infinity categories. I mean, maybe the first one is higher topos theory. Where basically the definition of infinity category is given and some basic properties, which takes still a long time. And then the second part, I guess, is higher algebra. This is another book online. And in higher algebra, he defines this notion of stable infinity category. It's basically an infinity category analog of triangulated categories. So in particular, what this infinity category analog is doing is that we can find limits and co-limits in, say, dB, i.e. limits when co-limits exist. So in particular, like dBr is an object here, is a typical object. And certainly, triangulated categories, they carry more structure than just a category. So these things are maybe better behaved than just cat infinity. Like a stable infinity category is better than just an infinity category. And we can pack this up, so we can define cat infinity x as a subcategory of cat infinity, and this will be the objects, basically, stable infinity categories. And the morphisms are so-called exact functors. So something that preserves like this notion of a triangle. It turns out that cat x infinity is a pretty good category, but still not good enough to like, cut out this initial object. It's not clear if you work with cat infinity x that you'll be able to find an initial object in this category that I wrote down. So we need one more refinement, which is as follows. So definition, there's this category called cat perf. which lives inside cat infinity, X, which lives inside cat infinity. And here, this category is basically all stable infinity categories where, like, given, so this infinity category C, all projectors. So these are maybe morphisms between two objects in your category, C, C, such that P of P equals P, have kernels and co-kernels. Okay, this may be, again, maybe a little bit of a scary definition. We've actually already seen it, and it's equivalent to, well, we've seen it for the one, we saw it when we were defining maybe Grothendieck category of motives, but in any case, cat infinity perf, another way of writing it is basically all stable infinity categories which are maybe in the literature you can say idempotent complete. This is idempotent complete categories are in between abelian categories and something like triangulated categories. Or maybe another way of writing it is pseudo-abelian completed. So remember when we defined the category of Grothendieck motives, we passed to the pseudo-abelian completion after defining our homomorphism sets, which is the same thing here, I guess. But we did it for Grothendieck motives for another reason. We wanted that, like, the diagonal to be able to be split. Here, yeah, it's just a nice, turns out to be a nice category with enough descent properties. So in particular, there is a map, for example, there is a pseudo-abelian completion. Going from cat infinity X to cat infinity perf, which is maybe a joint, which is left adjoint to the natural inclusion functor. All these, like, notions of, like, being a joint and things like this are properly developed in Lurie's higher topos theory book. I mean, it takes, once you get the definition of what infinite category is, like, you have to, yeah, prove the basic properties, and it takes some time. Okay, so we've defined DBR. Well, not defined, but it's some infinity category of finitely generated projective R modules. We can also define for X a scheme, something like dB of X, where if we write X with an open cover of affines, some affine open cover, because this category, cat infinity perf, I mean, it basically has all limits and co-limits. So we can consider maybe dB of some UI1, UI2 intersection UIN, and just take a limit across all indices, I1, I2, IN. Because you want, I mean, this seems like the right definition because you want dBx to satisfy some shift. You want this functor dB to be some kind of shift. So you want dB as a functor between cat infinity perf to satisfy descent properties. Another thing is that, like, okay, dBx is certainly inside cat perf. But maybe the unbounded version, dx, is often not. So it's one reason why I said in the beginning that the unbounded version is a bit too big. So I said that, like, well, we want to look at functors now. Initially, I said we're interested in functors from cat infinity to abelian groups, just a general class of functors. And I said that cat infinity was too big. So the correct candidate is cat to work with cat infinity perf. This will have, these class of functors will have enough descent properties to basically, get that theorem out. So we're interested in functors like this, which are compatible with some kind of monoid structure. So the compatibility with monoid structure is, as I mentioned roughly, it's these functors f are equipped, not any functor, but it's a condition, I'm imposing it, are equipped with some natural transformation from the forgetful functor to omega infinity composed with f. So both of these functors are functors from cat infinity perf, let's say, to anima, which is forgetting the group structure. And K theory will be the smallest or the initial object in this category. So this, I can pack all these objects into a category, and K theory equals initial object. Okay, before this is like honestly true, I also need, like, these functors f should also satisfy some basic descent property. So f should, I mean, K theory satisfies, like, this Milnor square kind of descent, let's say. So f should satisfy, it shouldn't be any functor. I mean, if we just look at, for example, dBr of, and then dBs, I mean, if we take a Milnor square, rs to r over I, s over I, this gives, plugging in dBr here, like dBr should give us K theory here of dBr, and similarly for dBs and so on. And these K theories should satisfy some descent. So we impose some kind of descent on these functors f. So maybe I won't go into it, but f should satisfy some descent. Should map Cartesian squares to Cartesian squares, roughly. Okay, and now with all these loose definitions, like, this becomes a theorem Bloomberg Gepneg, I think. Maybe Glepneg, I'm not sure. And Tabuada, maybe from 2010. Oh, so the theorem, is like, once I have this definition, then the theorem is something like this. So the definition of K-theory. So K of R, in the sense of this Bloomberg-Glepnik tabula. So let's say BGT. Let me make that a bit more clear. K BGT of R defined as the K theory of dB of R. So here K, just to make it clear, K is a function from cat infinity Earth to spectrum, which is an initial object. And I guess the theorem of Bloomberg-Glepnik-Tabuda says that there is an initial object. So there exists an initial object. Which we call K. And now so this defines some kind of K theory for every idempotent complete category, which is a very general definition. But if we just cut out maybe for ring R what K theory of dBr is, then these things have like okay, let's just define it like this so far, and but I'm still looking for a definition which is like indexed by integers. So like what is K2 and K3 and so on. So this is a spectra, an object in spectra, which are basically topological spaces in some sense. So they look like topological spaces. So in particular, there is a natural homotopy functor here. So in spectr, let me write it here. In spectr, there exists a natural homotopy functor. Pi n. And then we can define K of n of R, so definition, to be pi of n of this K BGT. And this isn't like an honest, I guess, abelian group. Okay, and maybe one theorem is that these K groups coincide with K1, K0, K minus 1, etc. that we defined. And of course, like there are other definitions of higher K groups. So like one definition is from Quillen, and these also, coincide there. there is a lot of things that I did not like properly define. So in particular, like I mentioned that like the category of spectra is in some sense isomorphic to the category of topological spaces. This also needs to be like one would need to properly discuss this, but it's part of the infinity category of machinery, let's say. And I mentioned that like because of that, there is a natural higher homotopy functor pi n on spectra. So we can take pi n of this spectrum object. That also needs to be properly defined, but it's also part of this Lurie machinery, and the contribution of Bloomberg, Glepnik, and Tabuada is the definition, the correct definition that was written down here, just the board before, for K theory, this K object, and the fact that there is an initial object in this category of functors. Okay, let me finish with like some open problems. Open problems and maybe some computation. So, like, okay, it's great that we've defined K theory. There is still like a lot we don't know about it, and it's like there is a bunch of research topic on it. So I think it's a great. I personally don't work in K theory yet, but I think it's a great area to go into if you're thinking of doing research. I mean, it's just you're exposed to many different areas of mathematics at the same time. I mean, motives, number theory, etc. And just to give a sense of like how much work needs to be done, well, here is some facts. So first of all, let's look at an example of where K theory is known. So for finite fields, we basically understand it. Q, then basically K0, FQ, these were computed by Quilling. So I guess like before Lurie's notion of infinity categories, maybe what's also taught is like the Yoal version or the Quillen version of infinity categories, but like this is the reason why, because I mean Quillen worked in K theory, so he had to come up with the correct notions which capture all these morphisms. But it's another notion of infinity category which works, but not so popular these days, I would say. So K0 of FQ is Z. K1 of FQ. These can be computed basically by hand. There's not two, but maybe some reciprocity theorem we need. So there is some number theory going on in the calculations. At least, well, elementary number theory. And the even groups of FQ are 0, and the odd Q groups are some quotient. So for I greater or equal to 1, and negative K groups are 0. So again, as I mentioned, to compute this, you need some maybe quadratic reciprocity theorem, but I can't remember off the top of my head. Then when we move to integers, so like open, like even for integers, so for z, we don't know what K of z is, but we know some things. So like results due to Borel. So some random results. So K of 4K plus 1 of Z. This can have some torsion. Once you quotient out by the torsion, it's equal to Z for K greater than 0. And ki of z quotient out by torsion is equal to 0 for I greater than 0. Okay, and one theorem for lower k groups, so Matsumoto's theorem. If you recall, like from a couple of lectures ago, we defined this Milnor k group. So we had this km n notion for the Milnor k groups. Which was a much more down-to-earth definition. But in any case, so this was for a field, for k a field. And indeed, the second k group, as defined in this lecture, well, defined in quotes, but didn't really, I mean, if you take all those loose definitions, I guess, then the second k group of k coincides with the second k group, Milnor k group, which I recall was this quotient, where k cross is considered as an abelian group with the multiplicative group structure, quotient by 1 minus a. So that's an old theorem, I guess. Maybe some conjecture. Parson's conjecture. So for x, a smooth projective variety defined over a finite field so the higher k groups of x vanish up to torsion. I'm not sure what the intuition is here for this, so for I greater than 0. Yeah, unfortunately, I cannot explain the intuition behind this conjecture. Another conjecture. Maybe. Yeah, I'm not sure. Yeah, this thing here, it's basically motivic cohomology, as I wrote down in the beginning of the lecture. So it's maybe k of, it would be h of the direct sum along j of h of 2j minus I of x, z of I. And basically what Parsons is saying is that he wants all these cohomology groups to vanish. Should be replaced with a rational here. Okay, I'm not sure, but maybe these motivic cohomology groups surely appear in Beilinsen's conjecture. For L functions. So maybe you expect maybe some leading term to be 0. I mean, the L function of a smooth projective variety of a finite field is basically the Weil zeta function. The Weil zeta function, which appears in Weil's conjectures. So there is a crazy definition of L function attached to a motive, which is using Frobenius, but this L function is basically just the generating function for the points, for the number of points, right? So maybe like this L function is understood, but in some sense, at least the Riemann hypothesis of it, because that's what Delhi proved. But maybe one expects some kind of leading term here to be 0 or something, and maybe that's where Parsons' conjecture comes from, but I'm not sure. Okay, another conjecture is finite generation. Okay, yeah, maybe one thing I should mention is that like in this K-theory things, like as it's deeply connected to motivic cohomology, which is then connected via Berlinton's conjecture to like the location, no, not the location, but the leading terms of zeros and poles of the L function, which is like some analytic behavior. Like that's why I guess K-theory is very deep, right? I mean, these L functions have like a quite difficult to study notoriously, and K-theory is basically capturing information about like where these zeros and poles occur in some through this logic here. So it's one like selling point for like why one should study K-theory. So finite generation. So for a ring R, which is finitely generated, over Z, then the groups K and R should be finitely generated. So this is a conjecture, maybe natural, but again I cannot like properly give the intuition. And just going back to this logic of K-theory, like we have like leading term of L function, which is like some analytic property. And on one hand, like we have motivic cohomology maybe defined through some kind of algebraic cycles things. And we have K-theory, which is like defined through vector bundles. So we have like two different points of view for the L function. So yeah, the K-theory basically adds like an extra information maybe that's hidden in some sense that if you just work with algebraic cycles. So yeah, if you want to study maybe Berlinton's conjectures, then you should try to have as much information as you can. And one of them is coming from motives or algebraic cycles, and the other one coming from, say, vector bundle information. So that's another selling point for K-theory. Okay, maybe related to all this is one more conjecture that I write down, which is the Berlinton-Soule conjecture. Soule, Banch. So for X, a smooth variety. For all I negative, then the hi of x of z of n is 0. I'm not sure, maybe it doesn't quite look right to me. Yeah, okay, maybe it's okay. So yeah, you expect low cohomology, negative cohomology groups to be 0 naturally, but actually like this is not known, and clearly this statement is related to some K-theory statement via this logic here, well via Bloch's, yeah, let's say Bloch's theorem. Okay, maybe I will stop there.